Hello, Riley Ruffin here, and we're getting ready to do our second demonstration for our physics class. If you'll note, we have a few items here. We have my famous mason jar, and in this mason jar I have it's just a little over 4 ounces of water. If I fill this mason jar up to the top with 16 ounces, then it would be 1 pound of water. So we have, well, about probably 30%. So about a third of a pound of water. I have a thermometer in it. This is a Celsius thermometer. Temperature of the water looks to be about 20 degrees Celsius. So my T0 is 20 degrees Celsius. And if you'll note, your formula sheet has conversions from Celsius to Fahrenheit and vice versa. So we will probably do some calculations converting Celsius to Fahrenheit as well as Fahrenheit to Celsius. Now I will, yes, it's still about 20 degrees. I will transfer the water content into this paint can. Paint can only is empty right now, has only air in it. And now I'm going to transfer the third of a pound mass of water into it. And we'll turn the hot plate or heating device, turn it on. Okay, I've turned on the hot plate. I can feel it heating up now. It's probably about an inch of water in the can. I'll record the temperature. I've started a timer also. So at T0 we had 20 degrees C, and as we progress through the experiment or demonstration, we will record temperatures. I expect the temperature of the water to reach about 100 degrees Celsius, which is 212 degrees Fahrenheit. I haven't calibrated this thermometer. This thermometer has a range of minus 20 degrees C up to 150 degrees C. So it's well within the range of the temperatures we should see during this demonstration. And I see the temperature actually rising. We're approaching 30 degrees Celsius at this time. Now, while the water, the can are both heating up, we can talk a little bit about heat transfer also. So the hot plate has a conductor that is allowing current to flow through it. And that conductor is, well, it's turning red right now. So it's generating heat. So I have a certain amount of current flowing through the conductor. And this hot plate is about 1,000 watts. It's plugged into an outlet that's about 120 volts. Let's say on average 110 to 120 volts AC. And if you we'll do the voltage calculations, which we don't talk about voltage and calculations or basic electricity in our physics class. But if you did the calculations, you would be able to tell how much current flow we have going through this hot plate now to actually generate this heat. Temperature is currently about 55 degrees Celsius. Now, let's talk a little bit about heat transfer. So I have the heating coil. The can is sitting on top of the heating coil, not the very bottom of the can, but the very bottom of the can, or the floor of the can, is actually raised, and you have seams where the circular or cylindrical part was attached to a circular part, which would be the end or the bottom of the can. So you have heat transfer occurring between the heating coil and the edges of the can, but that's being transferred through to the water. Now, as the water begins to heat, you will have another type of heating mechanism that will occur. From the heating coil to the can, since it's direct contact, that would be conduction. The molecules of the heating coil are vibrating even more. Since we're applying energy, they're vibrating even more, spinning even more, oscillating even more, so that now my kinetic energy is actually increasing. Well, that kinetic energy from those molecules is being transferred to the can's molecules, and the molecules of the can are now beginning to vibrate, oscillate, and spin faster. So the velocity of those molecules are now increasing or rising. And that's the change in kinetic energy that we're seeing. Now I'm starting to see some bubbles form in the water. Temperature is currently about 84 degrees. So my T1 is about 84 degrees Celsius. And we're about 6 minutes, just shy of 6 minutes into the demonstration. Temperature still rising, just shy of 90 now. And I expect us to have a rolling boil. In fact, I do see some boiling on the very edges of the floor of the can. And the reason why is because the heat is being transferred at the seams. So that's going to be the hottest point, is at the seams. I don't have my thermometer at the actual seams. I have it sort of probably about an inch or a quarter of an inch from the seam. So now I've put it at the seam. Temperature is reading about 91 degrees. And I do have boiling occurring. Now I have a rolling boil. You should be able to hear the rolling boil. Temperature is about 93 degrees Celsius. I'll take that as my temperature 2, my T2, 93. I do have a rolling boil going. We are 8 minutes into the demonstration. So what this tells me that my thermometer is not calibrated. It's about 7 degrees lower than it should be, because water boils at 100 degrees C at 14.7 pounds per square inch atmospheric pressure. So I'm 7 degrees shy of that now. Yeah, it's holding at 93 degrees, slightly above 93 degrees. And I do have a nice rolling boil. I don't know if you're able to see the vapor. I'm going to use this dark backdrop, so you should be able to see the vapor rising from the can, which is steam. So now we have used our heat transfer from the heating coil to the seams of the can through conduction, through the mechanism, heat transfer mechanism of conduction. The water is boiling, and as the water boils, that is convection. It's turning to steam, and as the steam rises from the can, that's also convection, because it will eventually heat up the area outside of the can. And so the heat will no longer be quote unquote localized in this area, but it will start to spread throughout this room. Okay, our temperature is about 94. I have a good rolling boil now. So what I'm going to do, I'm going to drop a cube of ice into our can that's boiling, and we'll see what happens. Regular ice, dropped it in there. All boiling ceased, so there's no more boiling. Temperature dropped down to 90. It was at 94, so my T3 was 94. Temperature after addition of the ice has dropped down to 85, 84, 84, 83. So temperature slowly dropping. I don't see the ice any longer, so it appears that the ice has melted. Looks like the drop stopped about 82.5 degrees Celsius. So I'm going to record that, 82.5 degrees Celsius. And it's holding steady there. '82. And now I'm starting to hear the can may be getting ready to heat back up to start boiling again. Now, and the reason why that I wanted to look at that is because that's demonstrating that even though I've got boiling going on, if I introduce ice, and ice requires a certain amount of heat to go from solid to liquid, that amount of heat was removed from the boiling process. So if that amount of heat was removed from the boiling process, it would stop the boiling process, which it did. It stopped the boiling process and started a melting process. So we will look at a phase curve, a thermal phase curve, and we will walk through that process of moving from solid, liquid, vaporizing, well, solid, melting, liquid, vaporizing, and then becoming superheated. So we're starting to boil again now. Temperature starting to rise. It's back up to about 90. And we don't have a full rolling boil yet, but it's won't be long before we have a full rolling boil. Okay, it's back up at a rolling boil now. Temperature's about 93, slightly over 93 degrees Celsius. I will drop another cube of ice in. Yes, we got a nice rolling boil now. 93 and a half. I'll drop another cube of ice in. Temperatures at 93, starting to drop. There is no more boiling occurring. Ice is melting. And the reason why I wanted to do that again is to talk about BTUs. So there's a certain amount of calories, or BTUs. Calories if you're looking at it in the metrics. BTUs if you're looking at the English standard units. There's a certain amount of BTUs that's used to heat, melt, raise the temperature, boil, and superheat. So we're actually talking about visible changes in the substance, but there's also changes with the amount of energy that I'm putting in. You know, we talked a little bit about, I think it was our first day, we talked a little bit about enthalpy. Well, I'm putting enthalpy in this water. The amount of BTUs that we're adding changed the ice to liquid, and I saw a temperature change as a result of that. Now, the temperature change that I saw represents a certain number of BTUs. Now, once that ice was fully melted, then the temperature started to rise again. So from ice, temperature would rise until the ice, well, it would still be ice, but temperature would rise to the point where it would reach its melting point, and then temperature would stay the same until all of the ice was melted. Then at the point that all of the ice was melted, you would start seeing temperature rise again. So when you can see the temperature rise, that's called sensible heat, because I can see it. It's something I can sense. I can look at it and watch it rise. When ice is melting, or when a substance is melting, that's called latent heat. That means that the heat is hidden in that you don't get a temperature change. Once all of the ice had melted and now it's all liquid, I should start to see temperature increase again, and that's exactly what we observed. Now the temperature is going back up to 90. We're starting to have a rolling boil again, or it's hadn't made a rolling boil yet, but it's getting close to a rolling boil. Now, what I would expect after that is the temperature, once all of the liquid has as much heat as it can hold at atmospheric pressure, it will boil like it's starting to do now. And until all of it boils and becomes steam, the temperature will remain the same. And we'll show that on our phase diagram when we get to our thermodynamics section of physics. So our water is now boiling, have some convection going on, steam is coming off, and what I'm going to do now is cover our can with this lid. I don't see any steam coming out from under the can lid now, but as pressure builds up, now I'm starting to see steam leak from the lid of the can. I don't know if you can see that, but let's see if we can give our backdrop again. There we go. I think you can see it now. Now our water level inside the can went from probably about an inch or so. It's probably down to about 1/3 of an inch now, maybe 1/4 of an inch, and it's still boiling. Now before, when we did not have the lid on the can, as the steam would rise, air would come in behind it and backfill, if you will. So as the steam would leave, air would come in. Now I've got a lid on it, so now air is not coming back into the can. So now I'm filling the can with steam because the pressure inside the can is higher than the pressure outside the can. And so that's why the steam is leaking from around the lid. Okay, now we have the lid on, we're steaming, and I'm going to turn our hot plate off. I'm going to move it to a safe location here. I will take the can, and as you can see, I do have my gloves on. I will take the can. I am going to seal this can. And if you could tell the difference in the pitch, as it got tighter, my pitch of the metal started to go up. Now you can see the can. I'm spinning the can so that you can see it's still cylindrical. I'm going to place it on this ice to accelerate the process. And so we should see the process actually accelerated. I'm going to keep the gloves on since the can is at least, at a minimum, 212 degrees Fahrenheit or 100 degrees Celsius. And we will give it some time as it cools. I can hear the ice melting, and in fact see the ice melting, so there's some heat transfer taking place there as the ice cools the can. I hear some popping. We'll turn it again. Ooh. So now we see that the can is starting to deform. So, physics students, what's causing that? What caused that to occur? Now you see that I've got even more deformation. As it continues to cool, what do you expect to happen? You should be able to formulate some type of hypothesis or theorem of what will occur based on what you have seen. And the real question is, why did this happen? Why did we get this response? Why did the matter that we had, why did it respond like this to the stimuli? Heating, then cooling. And we can discuss that further in our class. Now I'm going to touch the can. It's probably about 105 to 110 degrees, I believe, Fahrenheit, which is 30 something degrees Celsius. But it's warm to the touch. And as it continues to cool, what do you expect to happen? Thank you.